So the title of today's talk is 2 Decades of Low Rank Optimization. So Sam chose a title that makes him sound old by saying 2 decades, but I will say I have had the honor of working with and being colleagues with Sam since we went to grad school together. So I've known him for 26 years. So I outdate this paper. So welcome, Sam, and thank you.
Thank you. Well, thank you so much, everybody, for coming. Thank you for those who are online as well. This title is a bit gets you sort of in a reflective mood. I have a couple of goals for this talk. Let me see if I can get the clicker working. A couple of goals for the talk. One is to provide a kind of an overview of an active area of research. This is the area of what's called low rank optimization at the intersection of optimization and machine learning. And I also, because it's kind of tied in with this award, I'll be giving this talk a little bit, a couple of months from now at a conference. I wanted to do a little retrospective on my thesis with Professor Renato Monteiro that Anne mentioned. And because it's 2 decades, and because you probably need some kind of joke or something to remember at the beginning of a talk, I wanted to show you a picture from that time. So that's me on the left there and my advisor. And I look at this and I think, a lot really can change. So here's my outline. What is low rank? Why do we care? We're going to talk a little bit about that kind of retrospective, what we did as part of my thesis, and then talk about substantial progress since that time in the last 20 years or so. And then I'll finish up with a few conclusions. So first off, what is low rank? Well, actually, I need to define what rank is. So imagine you have a matrix M that's got M rows and N columns. The rank of M is just by definition, the number of linearly independent columns or rows in the matrix M. I think roughly speaking, we can think about rank as sort of telling us how much information is in the matrix M. So if you have very low rank, you have just maybe one linear and independent column. You've just sort of got really just one column and a bunch of copies of that. But if it's a rich matrix, there's going to be high rank. And so that's one of the reasons we care about rank. To measure the rank, you need the singular value decomposition. And that essentially takes the matrix M and it factors it into 3 matrices, U times a sigma times a V transpose. The U and the V are orthogonal matrices that basically give you some basis vectors to work with. And the sigma in the middle is really what's important in terms of the rank. The sigma is a diagonal matrix, and on that diagonal matrix, you have a bunch of non-negative values. The rank of M, and those values are called the singular values. The rank of M is then just the number of positive singular values. You can also do what's called a thin SVD, which is basically you take just the number of columns you need in U, call that U tilde, and just the positive singular values in sigma, and you can get this kind of smaller factorization. Now, this factorization of the SVD is going to come back, and we're going to see it a bunch in the talk. Now, if you have a symmetric matrix where M is equal to MM transpose, you have a square symmetric matrix, then you can do a different type of decomposition called the spectral decomposition. It's pretty similar, except that V basically is equal to U. So you have U times lambda. Lambda is a diagonal matrix, and then U transpose. The rank of M is just the number of non-zero eigenvalues of the matrix. The lambdas can also be negative in this case. Now, you can also have a thin spectral decomposition, which basically just means that you look at just the positive eigenvalues and the positive eigenvectors. And again, this kind of factorization is something we'll see a lot in the talk today. Now, what does low rank mean? It basically just means that the rank of the matrix, the R, is small relative to the M and the N. You have relatively low rank. And that means you have a lot of zero singular values or a lot of zero eigenvalues. And what I think, and this gets back to the comment about having a measuring amount of information, it's a type of sparsity. It's a type of interpretability in your matrix M. So why do we care? I pulled a kind of a famous paper, a quote from a famous paper. Rex Fossil and Perillo in 2010, they were working with low rank matrices, and they had these good comments. Notions such as order, complexity, or dimensionality can often be expressed by the means of the rank of an appropriate matrix. And they give a few examples. For example, you could have a low rank matrix corresponding to a low degree statistical model for random process, a low order realization of a linear system, a low order controller for a plant, or a low dimensional embedding of data in Euclidean space. And this is where we start to get some connection with machine learning. Because imagine you have a huge data matrix and somehow it actually has low rank. It means that somehow it doesn't have it's existing in a big space, but you could actually summarize it in a much easier way. And that's one of the key things that we're talking about. I wanted to also show this screenshot from a recent paper that really dug into why we see low rank matrices in practice. So I highlighted a couple of items here. Matrices of approximate low rank are pervasive in data science, appearing in movie preferences, text documents, survey data, medical records, and genomics. So we just see low rank matrices all over the place when we're gathering data. And this particular paper wanted to ask, why in the world is that the case? So what they did is they built a kind of a reasonable statistical model and came up with the following conclusion, which you see down here. Hence, any sufficiently large matrix from such a latent variable model can be approximated up to a small entry-wise error by a low-rank matrix. So we see them in practice, and we also have good theory as to why they even appear in practice. Now, another reason that we care is that sometimes we want to optimize over matrices. So I'll show some examples in a couple of slides, but essentially, sometimes we're faced with the choice of, we have a bunch of different matrices we could choose from, and we need to find the best one. And in particular, if we're optimizing over symmetric variable X, and you constrain the eigenvalues, for example, you constrain the eigenvalues to be non-negative, then you'll often kind of magically get optimal solutions that have low rank. And this can be, for example, in finance or in statistics, if you're optimizing over the set of correlation matrices. Correlation matrices are any positive semidefinite matrix that is non-negative eigenvalues with ones on the diagonal. And if you're trying to optimize over that, you naturally get low rank solutions. And this actually, if you think back to linear programming, and I know a lot of people have taken that class. If you think back to linear programming, this is a generalization of the fact that when you're looking at a basic feasible solution, you have lots of zeros and relatively few positive entries. And there's a lot of theory that has been built up to understand when low-rank matrices occur in optimization problems. These are 3 papers that I'll refer to a little bit later as well. And this is a picture to give you some kind of idea of what we're talking about. Now, these 2 objects, they look like a samosa and a ravioli, something like that. These are feasible sets in 3 dimensions when you constrain the eigenvalues. So they're not polytopes. They're not like linear programming feasible solutions or feasible sets, but they have more of a bend to them. But the points that are at the corners here, those are the low rank solutions that you might care about. And when you optimize, you might tend to go there. And so that's why we care. That's one of the reasons we care. So just to kind of summarize, what does low rank optimization mean? It means that we're going to optimize over a variable X, and we're just going to constrain it to be low rank, rank of X less than or equal to R. And to summarize, those 2 reasons are it's important for modeling low rank data, and it's also useful when the low rank structure appears naturally, irrespective of the data. So those are the kind of the 2 reasons we care. I thought I would go ahead and connect it with more modern machine learning immediately. So I went to ChatGPT and I said, in 25 words or less, what is low rank optimization? So this is the internet's version of what I'm talking about. Low rank optimization is a mathematical framework for solving optimization problems that involve low rank matrices with applications in signal processing and machine learning. So that's another way to think about it. All right, so let me get some examples here. The very first example that I imagine a lot of you know about is a principal component analysis, PCA. So you're given a data matrix M. You want to find the closest matrix with rank at most R. And so essentially what you want to do is minimize the distance between your variable and M. And in this case, we've got a squared norm, subject to the rank of X being less than or equal to R and X existing in the same dimension space. There are different ways to think about this, but essentially this is PCA, where you're trying to get a lower dimension version of that data set. And this comes up all over the place. This is one of the first dimension reduction techniques that people learn in machine learning. Another one is robust PCA. So this is the same problem, but a slightly different version of it. So you're given a data matrix M, and what you want to do is find matrices X and S such that M can be decomposed, written as X plus S, and X is low rank and S is sparse. Now, if the S part is 0, you're essentially back in the PCA case. But if you allow some noise, what that's the S does here, it has a few entries that corrupt the signal, so to speak, then you get this robust PCA. And here's one example of how you could use that. So imagine you're doing video surveillance, and you've got basically a static scene. In this case, you're watching the railroad tracks, and then you want to detect when there's actual movement across the railroad tracks. And so what you want to do is be able to separate into the low rank part, the part that stays fixed, the part that doesn't have that much new information in it. You want to fix that, that's the X. And then you want to catch the noise, the part that just indicates motion. And so that's how you could do it. So this would be the M equal the X plus the S. And that's how you detect movement in the video. So this is the kind of thing that we can do if we are able to use the low rank condition on X. Another one is matrix completion. So imagine you're given a big data matrix, or rather I should say there is a big data matrix, and you know some of the entries in it, but you don't know all of the entries. This is typically a good example of this is preferences of users with movies. And what you want to do is find the best, basically the best fit low rank matrix that matches on all the entries. So you're given a bunch of entries, I would say all unknown entries, Mij. You want to find the smallest rank matrix that matches that exactly on those entries. And this comes up in recommender systems. There's a famous Netflix problem that related to this. Other companies like Spotify would use it as well. And you can even do it in things like wireless sensor localization, where you have a bunch of wireless sensors that are talking to one another. They get partial information about what other sensors are close by, but then you want to piece it back together to some kind of global picture using an approach like this. There's another example called non-negative matrix factorization, which is a little bit different. I've written it here a little bit different than on some of the previous slides. So here what we do is we're given a matrix M, and then we go looking for other matrices U and V, and we minimize the norm of M minus UV transpose, the norm squared. And then we also want to make sure that the entries of U and V are all non-negative. Now this is a little different. It's actually a low rank optimization problem. But what we're doing here, the variable is actually in the factorization, or I should say, the variables of the problem give us the explicit factorization. And what you do is you force the columns of U and V to have just R columns. And what that does is it implicitly implies that the rank of this can never go above R. And this is very similar to that SVD, where we got the U and the V transpose. We're not really too worried about what the singular values are. But if you have this kind of factorization, you can guarantee that this guy never goes above rank R. And so that's the thing to point out here is that the rank is restricted explicitly just by construction. And so you don't have to put in the constraint specifically. This has applications in data clustering and feature extraction and things like imaging and text analysis and so on. Now, another type of problem that I've been working on over the years is something called quadratically constrained quadratic programming, which just means that you're going to minimize a general quadratic function subject to a bunch of general quadratic constraints. Now, this is a very broad class. It models all sorts of things like integer linear programs and polynomial programs and all sorts of things. So I'll just mention it kind of as a broad class. But one thing you can do with this problem is by introducing a new variable, capital X, you can actually turn this into a rank 1 problem. So a problem where it's you have linear objective and linear constraints, and then you have one condition that says capital X has to equal a rank 1 matrix. So this guy here is just a column vector times a column vector transpose or times its transpose, and this is saying that the matrix X has to be rank 1. So I won't go into the details here, but essentially this guy can be represented using low rank optimization too. Now, this gets me into a little bit of, I want to take a little bit of detour to talk about how people think about optimization these days, because it's relevant for the rest of the talk. And if you're like me and you learned about optimization in kind of the standard way, you first learn about linear optimization. And then maybe your next class is nonlinear optimization, where the first look is everything's linear. The second time you look at all sorts of nonlinear things. Now, what's become more common in like the last 2 decades is not to focus so much on linear versus nonlinear, but to focus more on convex versus non-convex. And here's a famous quote that a lot of people are familiar with. Terry Rockefeller is one of the big guys in convex optimization, convex analysis, I should say. And what he wrote back in 1993 was, in fact, the great watershed in optimization isn't between things that are linear and nonlinear, but between things that are convex and non-convex. And so with that, I wanted to show you some examples of convex functions. So this is an example where you might have a single variable X, and you're trying to find the minimum, the global min of this convex function. Convex functions are bowl-shaped. And in a bowl, if you imagine you're just like a little ant or a little drop of water or something like that in this bowl, to get to the bottom, you just go downhill. You just let gravity take you downhill. So it's not a linear function. It's not even differentiable necessarily, but you just kind of go down and you hit this global min. Convex functions are good this way. Non-convex functions are bad because you can get trapped in local max. You can get trapped in local mins. If you're here and all you can see is locally around, this looks great. It's not clear how you would then jump over and get to there to actually get the global min. So we like convex things, we don't like non-convex things. Here's another example of something that is convex on the left and then something that's very non-convex on the right. You have things like saddle points on the right as well, where in one direction it looks like you're a local minimizer and another it looks like you're a maximizer. So a lot of weird things can happen if you go into non-convexity. Unfortunately, it turns out the rank function is non-convex, and so low rank optimization is a non-convex problem. And in fact, it's NP hard, which means essentially that it's one of the hardest problems out there. But of course, it's still important. We'd like to be able to solve it. So people are interested in trying to understand how to do that. And so that gets us to our contribution, Renato Monteiro and I. And I will talk a little bit about how we got to this idea called the low rank idea. And it goes back to this quadratically constrained quadratic program that I showed you a couple of moments ago, where essentially previously I was saying that if you could solve this problem and set x equal to xx transpose, then you could solve this difficult thing called quadratically constrained quadratic programming. So what people have done is they've relaxed that problem into what's called a semidefinite program. This curly greater than or equal to essentially means that if you take the difference of capital X minus xx transpose, that matrix should have non-negative eigenvalues. And that turns out to be convex. So if you change that equality to this inequality, you've got a convex problem that you can solve. That is what's called SDP or semidefinite programming. And what we often do is turn it into some kind of standard form. So I'd actually like to focus on this standard form, a little bit separate from the first application. I'd like to focus on this one here. So what this is you're just minimizing a linear function subject to a bunch of linear constraints. The C and the AI are the data, and the X has to have non-negative eigenvalues. Now, in the 1990s, research on this and the interest in it really exploded. There were two main reasons for that. One was that people figured out that you could solve these problems in polynomial time using interior point methods. So it was a good class of problems to try to study. It's actually kind of interesting because you tend to get these types of interior point methods actually give you solutions with high rank. So that's a little bit of a contrast, just as a quick footnote. Another thing that was important was this approximation algorithm by Gomans and Williamson for the max cut problem. This came out in 1995, and it really generated a lot of interest in optimization in the computer science field as well. And so people started to try to solve bigger and bigger SDPs, and they realized there was some kind of bottleneck with interior point methods. They're polynomial time, but they practically have some challenges. And so I hope you like this phrase, at the turn of the millennium. That just means the year 2000. It sounds pretty grand, but around that time, researchers were trying to solve bigger and bigger SDPs, most often using first order methods. And the first order method just means that you're not going to ever take a second derivative. You'll just be dealing with first order information, first derivatives, and also function values. And there were a bunch of methods that tried to do this. This dual scaling method here was actually developed here at the University of Iowa. There was a spectral bundle method, another bundle method, nonlinear programming approaches. I was involved in another method. There were all sorts of approaches that people were trying to solve bigger and bigger SDPs. And then I, in particular, got into, besides doing a little bit here, I also got involved with what's called the factorization approach. And just to give a little bit more of a history, if you look at that Gomans-Williamson max cut SDP, what they did is they said their whole idea was essentially to take a matrix like this, UU transpose, and to replace it, to realize that that matrix could be replaced by a positive semidefinite matrix, X, which is semidefinite. And the U here, the U that they cared about in that application was square. So essentially it had full rank. So you had a square matrix times a square matrix transpose, and they replaced that with X being positive semidefinite. And that was one of their innovations. I mean, they had a bigger innovation in terms of the analysis, but that was one of the key ideas. And then someone came along in 1997, Pinato and Homer, and they said, well, if we want to solve even bigger problems, why don't we just optimize in the U? Let's not worry about the X, but let's just optimize in the U. And then we came along and said, well, actually, because of the way positive semidefinite matrices work, without loss of generality, you can essentially force the U to be lower triangular. So it's still square, but it only has entries in the lower triangular part. So you save roughly half the time, something along those lines. So this is how we got into this idea of factorization. So the idea was essentially, instead of working with the X, you work with the UU transpose. Now, these ideas seem to work in practice. We were able to solve bigger problems, but it was weird because the papers converted the convex SDP, a nice problem, into a non-convex problem. The UU transpose is a very non-convex sort of function. And it worked in practice, but the question was why? And we did have sort of one partial argument, and essentially the argument was, well, at least we know that these two problems are completely equivalent to one another. If you give me an X, you can get a U. If you give me a U, you can get an X. And so you can go back and forth. We had that kind of insight, but it still wasn't very satisfying. And so then finally, or maybe finally is not quite the right word, but we had this idea about how to use low rank approach. And again, we have this standard form problem that we want to solve. And then we realized that there was a theorem that was relevant. And basically it comes from the three papers that I showed you earlier. The one that's sort of most relevant, was phrased most clearly for SDP, was the last one by Pataki. And essentially what Pataki said is that there exists an optimal solution to this problem whose rank is no bigger, is strictly less than the square root of 2 times m. So no matter what the size of the variable x is, so x could be a huge matrix. If you have m constraints, then you know that there's a low rank solution whose rank is no bigger than the square root of 2 times m. And that was the key thing that we put together and said, well, that means that you could replace it with U times U transpose, where the U just has a few columns. And that's what we did. So essentially you write the big X as a thin U times its transpose, and you can basically get a more compact version of the X. But you just have to be willing to work in the U space. So that's what we proposed to do. And what we did in particular was take U having the ceiling of the square root of 2 times m column. So we just go high enough so that we make sure we have all the optimal solutions, or excuse me, we have at least one optimal solution of the SDP. We do cut off all of the high rank solutions, but at least we have an optimal solution according to that theorem. Okay, so we knew that we would be equivalent to the SDP because we didn't cut off all the optimal solutions, but we do have a very different feasible set. For example, we cut off all the high rank solutions. The potential advantage was pretty clear to us. Maybe you could save time and storage in terms of your algorithms, but would it actually work in practice? And I don't remember the exact day that, our discussion, Montiero was very nice to me. I would go by all the time and would talk to me as much as I wanted to talk. We thought, it couldn't hurt to try. And I went back into my old emails, which I actually still have, and I dug up the first time we ever talked about it. And it looks like the day was the 22nd of May, 2000. And basically I told, oh, and by the way, the time, just for any graduate students in the room, the time was about 11 p.m. And I told them I did it, I implemented it, and convergence is good. And of course, the computation and memory requirements are less. And then for any of the faculty in the room, my advisor wrote back right before midnight on the same day. And he said, it's really good news. Maybe we'll have some chance to compete with the other methods on some max-cut problems. So we were very motivated by just sort of having a fast code. And then I wrote back another day later, and I'd been able already to streamline it and get it roughly 30 times faster. So this was, some quick stuff that we were doing just to get the prototype out there, and it turned out to work okay. So
I like that I'm not kidding.
yeah. I also told him, I was a little bit bold. I said, if you come to school this afternoon, please drop by the computer lab. I was like calling him to my office. I probably shouldn't have done that, but anyway. Okay, so what were the computational results? We had success on specific classes of large scale SDPs. We looked at max cut, max stable set, and so forth. We actually also developed a code for general SDPs. And as I mentioned before, we only looked at first order methods. We never did anything with the second order, second derivative information. If you do that, you typically end up kind of, you get faster convergence, but you tend to slow down the iterations of your algorithm. We also experimented with other things like dynamically updating the rank, starting at small and increasing it a little bit. We tried to heuristically solve some NP hard problems using what we call rank 2 approaches, where you force the rank to be 2. So there's all sorts of little things that we tried. But in general, it was successful. And so to kind of summarize, what is the low rank idea? It essentially says, if you want to optimize over a variable X and you want to force the rank to be relatively small for a given R, then if your matrix is symmetric and positive semidefinite, then use the U transpose change of variables. If you have a general matrix, then you replace it with instead U times V transpose, where the U and the V both have R columns. So this can handle both the symmetric and the non-symmetric case pretty equally. Now, again, the question though is, why should this work at all? Because it seems to be going against the whole idea of convex is better than non-convex, because we're taking something that's convex and switching it to non-convex. So why should it work at all? And in the early 2000s, really, this did seem challenging to answer. We didn't have much idea. We did have one observation, was that essentially, if you're working in the U and the V space, you have a lot of degrees of freedom that allow you to move around in that space that do not affect what's happening in the X space. And it's a kind of a mouthful, but essentially it means that there's a Q transpose of the identity matrix written as an orthogonal matrix times its transpose can be inserted in the middle without changing the product of the matrices, but you change the matrices themselves. Now, that actually can be seen in some pictures, which I've got. I scoured through papers that talk about this. And this is an example of a low rank landscape that you're trying to minimize in about 3 dimensions. It's hard to do much visualization, but you can do some. So this is imagine that you're sort of on the surface and you want to get to the bottom. You essentially, wherever you start, even though the function is not convex, you'll sort of fall into one of these basins and you'll get to the optimal solution. And moreover, you have to look at the 3-dimensional picture, but these guys actually have the same objective value. So it does have a non-convex shape, but it's pretty easy to fall downhill and get to the optimal solution. This is very similar. I kind of think of this as the bottom of a wine bottle. You know how a wine bottle has that little thing at the bottom. So if you're trying to get to the bottom of a wine bottle, you just kind of fall down and you won't get stuck here. You'll basically get stuck in that basin. Here's another one. This is a very strange kind of wine bottle, but it has that same sort of shape. Here's another one. Now, it does turn out that you can have situations where the low rank landscape forces you to go down into one of these 2 optimal solutions. But there are cases where you can kind of tweak it and you can get local minimum. So the question is, when do you get this versus when do you get this? And that's what people have wanted to try to understand. This was actually another little artifact of my thesis. This is a screenshot from my job talk here in 2001, where I was looking at a low rank, rank 2 landscape. And here we were maximizing, but it had kind of a weird property where essentially you could get to a local max and get stuck here. But using that QQ transpose idea, you could rotate around and get here, and then you could escape out of that as a saddle point. So there's lots of weird stuff going on, and people have been interested in trying to understand, what do these landscapes actually look like? So we were able to prove, I wanted to just mention very briefly what we were able to prove theoretically to try to explain what was going on. And I'm going to give you this theorem sort of in pieces here. So imagine that the SDP feasible set is compact and it has interiors. So it's a kind of a bounded, well-behaved set. And consider the rank constrained SDP where you force the rank to be less than or equal to R, where R is greater than the ceiling of the square root of 2 times the quantity m plus 1. And you may notice that this is a little different than what I talked about earlier. It was square root of 2m and now square root of 2 times m plus 1. I'll mention why that is in just a second. And then we said, well, if you get a local minimum of the rank constrained SDP, and if the rank is actually less than R, so if you actually optimize, you get a local min, and you get a rank that's a little less than the R you're working with, then you can actually prove that that's optimal for the original SDP. And the reason we took m plus 1 is because we wanted to actually take a little more rank so that we were more likely to get a little less rank when we were optimizing. And that's one of the reasons we did that. And then we actually came up with an algorithm. We We look at the U problem. We solve the factorized problem in U via the standard augmented Lagrangian algorithm. So we pull a standard algorithm off the shelf, but with one tweak. We add a penalty term that is basically a very small epsilon times the determinant of U transpose U. This is a way to penalize high rank solutions. You have to kind of go through the details, but essentially this will prefer lower rank solutions by adding a very small penalty term. Then, and if you know the way augmented Lagrangian algorithms work, if at any step or if at every step we get an actual local min of the unconstrained problem, then our overall algorithm will converge to the global optimal solution U star. So there's a mouthful here, or it's a lot of what was going on, and it wasn't a perfect result. It was kind of a partial result. Some of the things that we wanted to really kind of understand better were things like this. Why did we really fundamentally have to take the rank a little bit higher? And actually, the things like the local min is a little bit of a problem because algorithms aren't actually guaranteed to go to local mins. They're guaranteed to go to second order stationary points, which are a little bit different because like a saddle point could be a stationary point, but not actually a local min. So we had some kind of strong assumptions here, but this was the best variable to do at that time. All right, well, that leads to a little bit of a concept called benign nonconvexity. And it's a reminder that nonconvexity is just not convex. There's actually functions like this where if you just keep falling downhill, it's not convex, but you'll still get to the global solution. So here you could keep falling down and it's not convex, but things are working out. You might have to get out of this saddle point, but essentially you can keep getting downhill. Here's another example. This is kind of like that wine bottle example where again, this is benignly non-convex because it is non-convex, but if you just head anywhere downhill, you'll get to the base. And it reminds us that usually when people talk about non-convex, they think about something like this, a really terrifying lion, but it turns out that it's something more like this. So this is kind of, we didn't really mean it, but this was part of what people started to call benign non-convexity. All right, so since then, what kind of progress have we seen? So just to give some idea, this is all up to maybe around 2003 or 2004, and then there's progress since then. I want to talk about some convex approaches, some approaches that still look at the low rank problem, and then ongoing work in benign non-convexity. Okay, so what have people done with convex optimization? So people are still interested in low rank. They want to solve the low rank problem, but there is a subset of the literature that only looks at convex optimization. And for that, one of the topics is this thing called the nuclear norm. The nuclear norm of a matrix is just by definition, it's the sum of the singular values of X. All the singular values are non-negative, so this is just the sum of a bunch of non-negative numbers on the matrix X, and this turns out to be a norm. So it has all the properties of a norm. It's called a nuclear norm. And moreover, it turns out that X star, or the nuclear norm, is what they call the convex envelope of the rank function. So the rank function is very non-convex, but you can underestimate it, put underneath it a convex function, and the nuclear norm is the best such function, the best such convex approximation when you restrict to just all the matrices that have nuclear norm less than or equal to 1. And so what people did is they took this nuclear norm idea and they came up with guarantees that you could solve the convex problem with the nuclear norm, and yet you would get the min rank solution that you want. You get the low rank solution that you want. So there's a number of papers that follow along in this vein. If you go into other types of problems, people have looked at sparse PCA. So that is PCA where you force zeros into some of the principal vectors. You can solve that with SCP. There's another class of algorithms called sketching algorithms where actually they solve completely the convex SDP. Everything's convex, but somehow they do it with storage that is equivalent to a low rank algorithm. So they kind of get the best of both worlds is one way to think about it. That's called sketching. And then there's other links between low rank matrix completion and what's happening in terms of the zeros of the matrix. So if the matrix is very sparse, you can sometimes connect that directly to low rank matrices, but still using convex optimization. So there's all sorts of techniques that one can do. Now, in terms of still sticking with the low rank approach, so really working in the factorization U, There is something called manifold optimization that can be used to solve SDP. Manifold, if you remember, a manifold is something that essentially looks like Euclidean space locally. So it's not actually Euclidean space, but locally it looks like it. So you can do manifold optimization to solve SDPs. And there are techniques for escaping saddle points, which is kind of neat. You'd be able to identify if you're in one of these saddle points and then be able to move out of it. People have looked at optimization with orthogonal matrices. That's the Q times Q transpose equals the identity. And one example of using that is to find the closest low-rank correlation matrix. So imagine you have a big correlation matrix from finance or something like that, and then to find a low-rank approximation of that is one technique. People have also practically solved huge matrix completion problems using things like stochastic gradient. This is another, for people that are familiar with stochastic gradient, this is kind of an overlap area where first order methods and these kind of stochastic methods are overlapping with low rank optimization, but they were also able to get theoretical guarantees on convergence rates and things like that. In fact, that's another type of thing that people have looked at in other cases, convergence rates for convex functions of X. And you can even do things like, even if the landscape has some non-convexity, you can do things like cleverly initialize, get some particular first point so that you're guaranteed to go to the global optimal solution. So they even know ways for particular problems to avoid getting stuck in local minima, even though those local minima exist. People have proved that there actually knows what they call spurious local minima in certain types of problems in the low rank space. And there's also convergence rates for things like block coordinate descent, where you might do optimization over one column of the U and then another, and then another, and then another, and then keep doing that over and over again. So people have looked at all sorts of little aspects of how the low rank approach can work. Now, if we go back to standard form SDP, remember that minimize CX, AIX equal to BI, X positive semi-definite. Back to that, that standard form problem. Here are the types of results that people have found since then. And this was where we had the kind of limited theoretical results at the time. So in 2016, Bumal, Voronitsky, and Bandera proved that for almost all cost matrices C, the first and second order necessary optimality conditions are sufficient for global optimality. If you study nonlinear programming, you know that the first and second order necessary conditions for optimality are really important. It tells you basically that your first derivative has to be 0 and your second derivative has to be concave shape for a local min. And usually that's not sufficient enough to tell you have global optimality, but in this case, it is sufficient. And this is really, I think, to me, this is one of the key results that really helps you understand what's happening in the low rank case, because it says you just do your algorithm, and if you satisfy the first and second order necessary conditions, then in fact you're global optimal. There's another type of analysis called smooth analysis, and it's actually been proven in 2021 that the low rank approach actually solves SDPs in polynomial time up to any desired accuracy using this kind of analysis. Smooth analysis allows you to kind of perturb the objective function a little bit. And to me, this is an amazing result as well, because it says, I mean, interior point methods are one of the methods that people liked for SDP because it worked in polynomial time. It turns out the low rank method in this analysis also works in polynomial time. And finally, just in 2022, now you might have noticed in both of these results, this is for almost all cost matrices C. This is smooth analysis, which allows you to kind of perturb the C. It turns out that there actually do exist specific C such that the landscape does have some local minima so that it doesn't turn out to be nice. So there's some really weird things going on here. Basically, the first two say it should work in most cases, but there are some weird cases where it doesn't actually work. So that's where we stand currently with this type of analysis. Now, in the last couple of minutes, let me mention some stuff about benign nonconvexity, because this has taken on a little bit of a life of its own, or a big life of its own, I should say. And there's a webpage by a guy named Drew Sun at University of Minnesota, CS department, as a matter of fact. And he has a big webpage that he's been maintaining all the way up till December 2021, where he just lists all these papers that talk about benign nonconvexity, and he breaks it down into about 21 different topics. So I've just got them alphabetized here, but you can just scan over and see some interesting topics. So here's a topic involving what we're talking about today. There's also deep learning, dictionary learning, phase retrieval, numerical linear algebra, all sorts of areas where things that are non-convex actually have guarantees as if they were convex problems. I also took a look at his webpage, and I looked at the years and how many papers he was reporting for each of those years in this benign non-convexity. And you can see down in 2010, it was 1 or 2, and then it grew all the way up to around 250 in 2019. So a lot of interest in benign non-convexity. And then, of course, I mean, not to undercut my own presentation, but then there seems to be this big drop off. I actually think he got tired of collecting all this, and he just doesn't do it anymore. So, I mean, it's not updated anymore. And I think this is still a very active area. And in fact, that's basically where I would like to stop, just to conclude, to think about the goals I had. I think the low rank idea has really turned out to be a pretty simple, powerful, and intriguing technique. Intriguing, why should it work, and why? How does this all look, and so forth? How fast do things converge? There's lots of interesting applications in optimization and machine learning as well. Benign non-convexity is an important idea. I think it's something that could be a nice area to explore. And then last but not least, I'd like to say thank you for indulging me in this trip down memory lane. So thank you very much. And I'll take any questions online or offline or in person or on Zoom, however it works.
Hey, Sam, is there such thing as a duality theory in SDP?
A duality theory?
That's right.
Yes, absolutely. It has a very rich duality theory, not quite as easy or as nice as like linear programming duality theory, but there's full duality theory worked out for SCP. And in fact, that's one of the key ways that you prove anything about low rank optimization in those cases, is you have to somehow connect it back to the dual solutions. And so that really does play an important role theoretically.
Hi, Sam.
Hey.
So, I think most of the examples you use, talk on linear SDP. I wonder how much of this result can be extended when the objective function is nonlinear. Does it require any behavior of the objective function?
So there is a little bit of work that's done with convex functions. So you optimize a convex function of x, and then you only require that x be positive semidefinite. So there are some conditions there. They basically try to look at just sort of the standard conditions that people look at with convex optimization, strongly convex and so forth. Now, one of the things that might be missing in those cases is the existence of a low rank solution. So sometimes in a convex situation, you might necessarily be optimizing and get a very high rank solution. And so this may not apply, but there is some work on that. Yeah.
Are there any questions on?
Oh.
I will just point out, hey, I think this is the same room of your job talk.
I remember.
I think it's this room.
I remember being up at the big room because I was terrified. So.
And also the thing at the bottom of the wine bottle is called a punt.
Oh, okay. I did not know
The berry.
Just so you know.
I did not know that.
You had a slide that said something like there are specific C for which the conditions about the first and second order
Yes.
conditions don't apply global optimality. Do you have an idea about the cardinality of the set of those C's?
I think it is infinite in the sense that it's parameterized just by a few scalars that you get to change around. So I believe my recollection is the way they constructed it. I mean, when you look in the paper anyway, they just say, here's a set of matrices C that have this property, and there's a lot of room of flexibility in there, but it's measured 0. So in other words, it doesn't take up space, but it actually, there are an infinite number of them.
Great. And I will say thank you once more to Sam.